All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, and so topic for today, we're starting our final set of lecture notes, which is isoparametric elements. So I'm hoping to be done by Thursday of this week. If anything spills over, we'll talk about it next Tuesday. But right now, I've left the entirety of next week completely open. And so the hope is that you guys are starting to work on your final projects. You do have everything you need for part one of the final project, so you guys can definitely get started with that. Part one, I think, is the most satisfying because it's, I think you kind of go from a relatively blank, file of code, and you write in it, and then you get something where you compute a finite element solution. So yeah, I would definitely get started with part one. As we discussed this week, this will give you the information for part two and part three. And so the idea is that, hopefully you'll have everything you need to write the code so that next week, whatever questions or whatever debugging that you need to do, we'll have kind of open office hours during the lectures to do that. Okay. Okay, so that's the plan for the rest of the semester. We are very quickly approaching the end. We only have four more class sessions together, including today. Okay. Midterm two exams, and so I am on track to have them returned to you guys by Thursday. I've already graded a few of them, but I'm basically gonna be grading them tonight after my son goes to sleep, and then tomorrow as well. So should be good to go by Thursday. So if you want to come to class on Thursday, then they should be there as well. Okay. I wanted to finish by Thursday just because I know some of you will be going to the alumni event after class on Thursday as well. So a lot of you will be here in the class anyway for that, and so I wanted to return it to you that day. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So last time we were here was about a week ago, so that was kind of before the midterm. And at that time we were talking about numerical integration with Gauss quadrature in 2D. Okay. So, we've already introduced Gauss quadrature, right? So we already kind of have talked about its 1D counterpart. Okay. So in 2D, we're just aiming to evaluate double integrals numerically. Okay. And this is really helpful because, when we work through the derivation for our finite element forms, for our weak forms, there are usually a lot of integrals that we need to evaluate. Okay. Okay. So we need to do an integral for the element stiffness matrix. We need to do an integral for the body forcing term or the thermal generation term. We're going to need a Gauss quadrature integral for the Neumann boundary conditions as well. Okay. So there's just always a lot of integration that needs to be done. And so having a technique or having a method to evaluate these numerically, especially in code, is something that's very helpful. Okay. So the basic idea is still the same, right? The basic idea for Gauss quadrature is we're going to take a double integral. It has to be a double integral with the bounds being -1 to 1, okay, of some function, right? So f of x, y here is some multivariable function, which is a function of x and y, okay? And so what we can say is that, through Gauss quadrature, we can say that the value of this integral is approximately equal to, okay, the summation of I is equal to 1 up into the number of Gauss points. Okay. So that's summation from I is equal to 1 to NGP, where NGP is the number of Gauss points that we choose of our function. Okay. right? So that f of xi, yi there, that is our integrand evaluated at the Gauss points. Okay. Right. So the whole idea is not to perform the antiderivative. We just take whatever's in the integrand and we just evaluate it at our Gauss points. Okay. And then we need to multiply this by the corresponding Gauss weights. Okay. This Wi here, these are our Gauss weights. Okay, so our integration becomes just a simple weighted sum. Okay. Okay. So we like using Gauss quadrature. So remember, Gauss quadrature is not the only method for numerical integration in 2D, but we like to use Gauss quadrature in finite elements because it is very, very efficient when our integrand is a polynomial. Yeah. And what I mean by efficient is that we achieve a high level of accuracy without too many Gauss points. Okay. Because the cost of a Gauss quadrature increases the more points that we are going to be using, right? So whether we use 1 point or I don't even know if it goes this high, but or 25 points, right? It's going to be a lot easier to do the 1 point Gauss quadrature versus the 25. Okay. But if our integrand is a polynomial, which often it is, because because of the way finite elements is formulated and our shape functions are, Gauss quadrature will achieve accuracy with just a very few number of Gauss points. Okay. Okay. All right. So that's the basic idea of Gauss quadrature, right? So in 2D, there are kind of two different rules that we'll use. We're not going to go beyond this just because it's it becomes just kind of overkill at that point. Okay. So the simplest one we can use is just a simple 1 point rule. Okay. Right. So the 1 point Gauss rule refers to the fact that we're going to evaluate the integral with just a single Gauss point. Okay. Okay. And so the Gauss point for this 1 point rule is 0, comma 0. Okay. Right. So xi and yi are both 0, and then the corresponding weight is 4. Okay. And there's only one of them just because it's a 1 point rule. Okay. All right. So basically what we're saying is that, if we have our integral here from -1 to 1 of f of x and y dx dy, this is approximately equal to 4 times our integrand evaluated at 0, comma 0. Okay. All right, so this is the absolute simplest that you can do, right? And so it only requires 1 point. In fact, that point is right smack dab in the middle of the domains, which is very convenient. Okay. Okay. So I would say, for 1D problems, usually a 1 point rule is usually enough just because you're working with pure linear functions. In 2D, it gets a little bit more complicated. You could end up with, functions that are not purely linear. And so the one that's actually used most often is the 4 point rule. Okay. Okay, so the 4 point Gauss rule will utilize 4 different Gauss points. Okay. right? And so I'm going to label them point 1, point 2, point 3, point 4. Okay. So this right here are the Gauss points. Okay. So point 1 is going to be minus 1 over root 3, minus 1 over root 3. Okay. Point 2 is going to be a positive 1 over root 3, minus 1 over root 3. Okay. Point 3 here is going to be both positive, 1 over root 3, 1 over root 3. And then point 4 here is going to be a minus 1 over root 3, positive 1 over root 3. Okay. Okay, so if you plot that out, okay, so there's our square domain, right? So our square domain goes between minus 1 and 1. Okay. So these four Gauss points are kind of approximately, not quite, but approximately kind of in the center of each of the four quadrants here. Okay. Okay, so this would be Gauss point 1. Okay. This here would be Gauss point 2. This here would be Gauss point 3. And this one here would be Gauss point 4. Okay. Okay, so you're basically going to evaluate the function in each quadrant, essentially. Okay. And then the weights. Okay. The weights are actually very simple. So the weights are just going to be 1 all the way down. Okay. So that's the 4-point rule, right? So you're going to evaluate the integrand 4 different times. Unfortunately, we have irrational numbers here for the Gauss points, but that's just kind of how they derive to be, for to reach maximum accuracy. Okay. All right. So not too much to discuss here. So 2D Gauss quadrature not too different from 1D. It's just that we have just an extra dimension here. Any questions on this before we do a quick example of 2D Gauss quadrature? Okay. All right. So let's do a very quick example here, just so you can kind of see how this works out. Okay. Okay. So let's say we want to evaluate the integral. Okay. So we have integral from minus 1 to 1, integral from minus 1 to 1 of x squared y plus 3 dx dy. Okay. Right. So fairly simple function, but it is a multivariable function since we have both x and y. And what we're going to use here is we want to use a 4-point Gauss rule. Okay. All right, so this is pretty simple. We're basically just going to take our integrand, and everywhere we see x and y, we're going to plug in the appropriate Gauss points, okay? But first we notice, right, our bounds here are perfect, right? Because remember, Gauss quadrature will only work if you're integrating between minus 1 and 1. Okay? All right, so all the conditions are met here, so let's go ahead and apply our Gauss quadrature rule, okay? So this function right here, x squared y plus 3, this is our f of x and y, okay? So to evaluate our Gauss quadrature here, we're going to have basically we're going to evaluate this integrand here, f of x and y, at each of the Gauss points that we have up here, because we're using a 4-point rule here. Okay. Okay. All right. So we're going to take the summation of all of these. Okay. All right, so first evaluation here, we're going to evaluate it at -1/√3 for x, -1/√3 for y. So this is going to be a -1/√3 quantity squared multiplied by -1/√3 plus 3. Okay. Okay. Plus same thing, but instead of our x value being -1/√3, we're going to have a +1/√3. Okay, so we have 1/√3 positive squared times -1/√3 plus 3. Right, so this quantity right here is f of -1/√3, comma -1/√3. This quantity right here is f of +1/√3, -1/√3. Okay. Plus, same thing, but both our x and y are going to be +1/√3. Okay. And then finally, we have the last part here where the x is negative and the y is positive. So -1/√3 squared, 1/√3 plus 3. Okay. All right. So these last two terms, this one here is f of +1/√3, +1/√3, and this one right here is f of -1/√3, +1/√3. Okay. All right. So it looks scary here, but you're going to see that a lot of this is actually going to cancel out. Okay. Okay. All right. And so you see here, if we look at this, right, we have this quantity and this quantity here. Okay. So both of those are going to be a -1/3 raised to the 3/2 power. Okay. So we have a minus sign for that. And then both of these terms are going to have the exact same magnitude, but they're opposite signs. So they're all going to be positive. And so these terms are going to cancel out with those terms, right? So all the scary radical terms for this particular problem are all just going to go away. Okay. All right. And so we perform the integral. We just have 3 plus 3 plus 3 plus 3. All of our weights here are 1. Okay. Because that is our rule for the 4-point rule. Right. So we have 3 plus 3 plus 3 plus 3, which is 12. Okay. Okay. So gas quadrature, pretty straightforward here. It's just, it is a little bit tedious to do by hand. And so the trick here is going to be to write computer code to do this for us. Okay. All right. Any questions on this so far?
The weights are always 1, right?
So for a 4-point rule, the weights are always 1.
Oh,
Yeah. So all 4 points, the weights are 1.
okay. It's just that the bottom weight, it just looked like a negative. I missed that, so I
Oh, I'm
thought
sorry.
like,
Yeah, that's I meant that to be a dot, so it's a multiply by 1. Multiply by 1. It still looks like a negative, but there we go. Parentheses. Mhm. Yeah, so for a 2D Gauss quadrature, all the weights should add up to 4.
okay.
Yeah, so no matter which rule that you use, they should add up to.
Unlike 1D where it added up to 1.
For 1D, they add up to 2.
Sorry.
Yes. So 4 is an interesting number, actually, so it's actually good you brought it up, right? And so if we look at our domain here, right? So our domain, if we look at this, right, we have basically the square here, where if you actually measure the length of each side of the square, right? Because each side of the square goes from -1 to 1, each side length is 2. Okay? So that means the area of this square is 4, right? And so the weights are there to kind of sum up to whatever the area of that square is. Yeah. Not essential knowledge, but I think neat. So just a little neat trivia with Gauss quadrature. Okay. All right, any other questions on this example? Okay, so before we move on, I do want to make a couple notes here. First one being fairly obvious, and actually it segues directly into our discussion of isoparametric elements, which we'll discuss next. Okay. So this technique or this Gauss quadrature, at least as just how I presented it here, only works when our integration bounds are -1 to 1. So I should say, maybe pure Gauss quadrature. Okay. And that goes for both X and Y integrals as well. Okay. So you literally have to be on this kind of perfect square with Simon's too. Okay. But of course, most of the time we're not going to be working on that square, right? Because eventually, we want to be able to use Gauss quadrature to develop our element stiffness matrices, but our elements could be oriented in a very arbitrary way. Okay. So we're never going to have a situation where the coordinates of our elements are going to match up exactly to what we need for Gauss quadrature. Okay, but we really like Gauss quadrature, right? So to say that we can get an integral here with just 4 evaluations is really powerful. And so we want to be able to make this work. And so the bridge that kind of makes the connection between Gauss quadrature and our 2D finite elements is going to be a change of variables, right? Right. So just like in 1D, right? So we need to perform a change of variables. So when our integration bounds or when our domain is arbitrary, it's not in the nice -1 to 1 Gauss quadrature. We need to change variables so that we can do that. Okay. But in 2D, the change of variables is actually quite a bit more involved. And so we actually give it a special name called isoparametric elements. Okay. Okay. And so that's going to be our last set of lecture notes, which will start very soon. Okay. The other note that I'll make while we're here is that this version of Gauss quadrature, it only works when our domain is rectangular or square. Okay? And technically, that's going to go for the isoparametric elements as well. So when we discuss isoparametric elements, we're only going to discuss it for rectangular elements. Okay. So our elements have to have 4 sides and four nodes. Okay. All right, so question in the chat. So triangle elements, which is the other common mesh shape, will have its own unique approach. It's going to have the same procedure, right? And so the same isoparametric procedure that we'll go through on the next in the next set of lecture notes, you're going to apply that for triangular elements as well. The difference is that the shape functions are going to be different, right? And there's technically only 3 shape functions because you have only three nodes. Right? So that's going to be your main challenge for the project is that, you're going to take basically the theory and then basically take the concepts for isoparametrics, which will be presented to you for rectangular elements, and then apply that to triangular elements, which is going to be what your project uses. You could make the argument that the triangular element is actually a little bit simpler than the rectangular one, because for triangular elements, if you recall from before the midterm, triangular elements don't have any of those cross terms. There's no pseudo-linear terms, and so your shape functions are actually much simpler for the triangular elements. Okay. I do outline that, and so if you read the project specifications, I go over the Gauss quadrature for triangular elements, and so we kind of glossed over that a little bit, when we first talked about the project, just because we haven't gotten there yet. But I think now that we're going to be discussing that this week, I think it's worth revisiting that again, just to kind of see what that is. Okay. You'll see the triangular elements there, they are simple. And I think, a lot of the questions I get for the final project, and the last couple of times I've taught this class is that, they ask me, is that it? Is it really that simple for triangular elements? And so yes, it is that simple for triangular elements. Rectangular elements they're just a bit more complicated because they have that pseudo linear term, if you kind of remember from the class. Okay. All right. Any questions on this before we jump into isoparametric elements? Okay. All right. So let's go and make the transition. So this is our last set of lecture notes. Okay. Okay. All right. So the topic is isoparametric elements. Okay. All right. So because we're kind of starting this in the middle of this lecture, there's a little bit less introduction that I have to do, right? So the main issue that we have, right? So we want to apply Gauss quadrature and we want to apply our weak form to a general finite element mesh in 2D. Okay. Okay. Right? Because so technically, in terms of equations, isoparametrics aside, the change of variables aside, right? We have everything that we need to actually solve arbitrary 2D problems, right? Hence why, I said that you can do part one of the project right away. Okay. The issue, of course, is going to be, when you create a 2D mesh, on an arbitrary 2D geometry, your mesh elements are almost never going to be, I would say, kind of well behaved. Okay? So issue. All right, so they're all going to have the same shape, right? And so, whether we're working with a triangular mesh or a rectangular mesh, right? So all of our elements will have the same number of sides, the same number of nodes, but they're all going to be oriented a bit differently, right? So you can kind of change a rectangle to be kind of any kind of shape that you want. Okay? All right, so for instance, right? So we may have an element that looks like this. Right, so maybe this is our rectangular element that was produced by the mesher in our system. Right, so we have basically an arbitrary rectangular element here. Okay? So this is exactly how the element would be presented, or this is exactly how the element would be configured in your mesh. Okay, and so what we say is that this element here is in the physical space or physical domain. right? Because that's exactly how the element looks, okay? But the issue here is that, when an element looks like this, right, doing the computations that we need to run a finite element method are very difficult, okay? Most notably, the integrals, right? So eventually, we're going to get to a point where we need to integrate on this arbitrary element. Okay. And that's really hard to do, right? So when we have slanted lines, our elements are kind of an arbitrary volume. The lines are going in arbitrary directions. This is a very difficult problem to actually integrate. Okay. So what we want to do instead is we're going to say, okay, we have this element here. It is very difficult for us to do computations on it, but what if we make a change of variables? Okay. Right? And so we change the variable so that we adjust the shape of our element to be something that's much easier to integrate, right? In particular, what if we change variables to exactly match the Gauss domain that we need to do Gauss plotting? All right, so let's say that we map it onto a perfect square here, right? Where the bounds of the square are going to be -1 and 1, okay? Right, so our nodes are still 1, 2, 3, 4, okay? So we still have to integrate on this, right? And so this is something we still have to integrate. But since we kind of went through the trouble of performing the change of variables, we're now in a domain that's much easier to do, right? So we can now use Gauss quadrature to do any kind of integration that we need. Okay. Okay. And so by doing this change of variables, we can do that calculation. Okay. So we have to give this domain a name, right? And so, if our original element is in the physical space, we can say that this is in what we can call it the isoparametric space. Okay. We can call it the standard space. But kind of the convention that's used in the literature in a lot of textbooks is we say this is the parent space. And this is what we call the parent element. Okay. I think it gets that name because, this is kind of the standard quadrilateral here. And we can basically morph this into any kind of shape that we want. And so this is the parent of all possible rectangular elements here. Okay. Okay. The other important thing I'll note in this figure is that, by performing this change of variables, we're no longer working in X and Y, right? So the physical space, our coordinates here are X and Y, right? So that's our standard XY Cartesian space. Okay. In the parent space, we call the physical coordinates something different. We don't call them X and Y. We call them epsilon and eta. Okay. Right, so epsilon is our horizontal axis, and eta, which is kind of and so epsilon is kind of like a very squiggly E, and then an eta is basically a fancy N. Okay. Right, and so we kind of make the distinction here between the physical coordinates X and Y and the parent coordinates epsilon and eta. Okay. Okay, so this whole idea, right? So this whole procedure of taking any element that's oriented arbitrarily, performing the change of variables, doing the Gauss quadrature there, right? We call this the isoparametric concept. Okay. All right, and then we're going to explain the details of this isoparametric concept for the rest of class today and Thursday as well. Okay, but that's the general idea, right? But of course, this is, so I think, conceptually, especially coming from where we've been in this class, I think this concept is, hopefully not too hard to grasp, but the devil was in the details for sure. And there are a lot of details with this with this concept. Okay, so before we start diving into that, are there any questions on this so far? Okay. All right, so let's go ahead and dive right in. Okay. Okay. Let's see where to start here. Okay. So first thing we're going to define is that for our parent element, well, first of all, since our element here has four nodes, that means we need four shape functions that's going to form our interpolation. Okay. All right, and so in fact, so technically, we're going to have shape functions both in the physical space and the parent space. Okay. So that means any quantity, so t, okay, of x and y is going to be equal to t1 and 1 function of x and y plus t2 and 2 function of x and y plus t3 and 3 function of x and y plus, I ran out of room, t4 and 4 function of x and y. Okay. And we're going to have the same kind of counterpart here with the same nodal values. Okay. Sorry, I forgot T1 on the first term. Should be T1 and 1. Okay. We're going to have the same counterpart here with counterpart shape functions for the parent domain. Okay. So you have T, which is a function of epsilon and eta, is equal to T1 and 1 function of epsilon and eta plus T2 and 2 epsilon and eta plus T3 and 3 epsilon and eta plus T4 and 4 epsilon and eta. Okay. Okay. And in fact, if you remember from our Gauss quadrature in 1D, we can use these same shape functions to provide a mapping from the physical coordinates to the parent coordinates. Okay. Okay. Because in order to apply our change of variables here, there needs to be a mathematical relationship that relates a certain coordinate in the physical space, x and y, to a coordinate in the parent space, epsilon eta. Okay? Okay. So for instance, right, our x coordinate, right? So our x relationship between x and functions of epsilon and eta, okay, is equal to x1, where x1 here is the physical coordinate of the first node in our original element here, okay, and 1 epsilon and eta plus x2 times n2 epsilon and eta plus x3 and 3 epsilon and eta plus x4 and 4 epsilon and eta. Okay. where these x1, x2, x3, x4, right? These are the coordinates of our nodes in our original physical space. Okay? Okay. All right, and then we can form the same thing for y as well, right? So we need a mapping between x and y. So our y mapping here is going to look very similar, except instead of x's, we're going to have y's. Okay? So y1 and 1, epsilon and eta, plus y2 and 2, epsilon and eta, plus y3 and 3, epsilon and eta, plus y4 and 4, epsilon and eta. Okay? Where these y1, y2, y3, y4, right? These are the y coordinates of our nodes in the physical space. All right, good. All right, so if you look back to your notes back in, when we discussed 1D Gauss quadrature and we kind of did that 1D change of variables, we had expressions that looked like these as well, right? They weren't as detailed or didn't have as many terms, because we were just working in 1D, but the idea here is the same, right? So the idea is to use these shape functions to form that relationship, right? So the mapping, basically the mapping from the physical space to the parent space will be done or facilitated by these shape functions. Okay. Okay. Good. Oh, you know what? I just realized I never gave you what those shape functions are. So those shape functions are not mysterious. We know exactly what they are. And in fact, when we define them in our parametric space or our parent space, they have very simple expression or relatively simpler expressions because our parent space is so very neatly defined here. Okay. Okay, so let me write out the expressions for the shape functions here. Okay, so we have n1 of epsilon and eta is equal to 1 divided by 4 times 1 minus epsilon, 1 minus eta, okay? And 2 of epsilon and eta is equal to 1 over 4, 1 plus epsilon, 1 minus eta, okay? And 3, third shape function of epsilon and eta is 1/4, 1 plus epsilon, 1 plus eta, okay? And 4 of epsilon and eta is 1/4, 1 minus epsilon, 1 plus eta. Okay. Okay. So I told you, right? Devil was in the details for this. And so there's just I think things just take a lot longer here just because we have functions of multiple variables. And we have four nodes in our element. So everything is kind of multiplied by four here just because there's four shape functions and four things that we need to do. Okay. Okay, so I know some of you are still writing this down, but let me kind of draw your attention to one interesting feature here. Okay. Right? Notice how these shape functions are formed here. Where if you look at every single shape function, we're going to have a term that's the product of epsilon and eta at some point, right? So it's either going to be positive epsilon eta or negative epsilon eta. Okay. So remember, this term here is unique because even though technically it's not strictly linear because we have the product of two independent variables, but we say this is our pseudo-linear term because it's linear individually in epsilon and individually in eta. Okay. Okay. So the presence of the pseudo-linear term is something that's unique to the rectangular element. Okay. So when you guys are doing your final project, the triangular element does not have the pseudo-linear term. And so when you're computing your shape functions, they're actually a lot simpler than this. And that means your shape function derivatives for the triangular element are also going to be constants as well. Okay. But part of what makes the rectangle so difficult is that when you do take derivatives of the shape functions, you don't end up with a constant. You actually end up with something that has a variable still in it, which makes the integration, more difficult. Okay. All right. Any questions on that so far? Okay, good. All right. Next thing that we'll do, right? So there's just a lot of writing in kind of this first phase, just because there's a lot we need to kind of pre-compute before we get into the method. Let's take derivatives of our physical mapping, right? So both our physical mapping x and our physical mapping y, both of those are functions of epsilon and eta, which you can define as our new coordinates, right? So we can take the derivatives of these functions with respect to our new coordinates. Okay? So we're going to take the derivative of our mapping function, so that's x of epsilon and eta, and y of epsilon and eta. Right? Since those mappings are functions of our parental coordinates, let's take those derivatives with respect to those parental coordinates. Okay. All right. And so, as we're writing this down, you're going to be wondering why are we doing this? I mean, you might already be wondering that for all of these computations we're doing. Okay. So for this step in particular, these derivative mappings we're going to use to form our Jacobian. Okay. All right, so hopefully that term rings a bell because that is something that we went over in 1D, right? So the Jacobian is something that's going to act as kind of like our scaling factor, right? The fact that, usually when you apply isoparametric elements or whenever you do a change of variables, the size of your integration domain is actually either going to grow or shrink, right? It's very rare that you end up with an element that had a perfect area of 4, right? But when you map it to our Gauss quadrature element, we're moving to an element with a area of 4. Okay. So the Jacobian kind of acts as a conversion factor based on the fact that the size of our integration bounds are going to be changing. So this is something that we needed in 1D, right? So the fact that in 1D our integration lengths were changing, we need the same thing in 2D. It's just that in 2D the expression is a bit more complicated. Okay. Okay. And so in fact, we have multiple derivatives that we need to take as well, right? Because we have two mapping functions, so we both have x and y, and each of those mapping functions are functions of two different variables themselves, epsilon and eta. So in total, we're going to have four different derivatives of our mapping functions. Okay? So I'll write out the first one in detail, but you can kind of, or I'll do the first couple in detail, but then you can kind of fill in the rest. Okay. Okay, so first we have partial x, partial epsilon. Okay. Right, so we're going to take the derivative of our x mapping with respect to the first parental coordinate epsilon. Okay. Right, so this is going to be, right? So the fact that, x1 and x2 here, let me kind of scroll up a bit. x1, x2, x3, x4, those are all constants, right? And so those don't depend on epsilon or eta because those are just the coordinates of our original nodes, right? So when we take the derivatives, those constants are just kind of along for the ride. And the only terms in the expression where we apply our derivative are going to be on the shape functions themselves, n1, n2, n3, n4. Okay, so we take this derivative, we get x1 partial n1 partial epsilon plus x2 partial n2 partial epsilon plus x3 partial n3 partial epsilon plus x4 partial n4 partial epsilon. Okay. Okay. So we can also take the derivative of our x mapping with respect to the second parental coordinate, which is eta, right? So we have partial x, partial eta. Okay. So that's x1 partial n1 partial eta plus x2 partial n2 partial eta plus x3 partial n3 partial eta plus x4 partial n4 partial eta. Okay. So just the main thing to note here is that all the derivatives are moved directly onto the shape function. Those are the only parts of this expression that depend on epsilon or eta. Okay. Okay, and then you can come up with similar expressions for the y mapping as well. So we have partial y, partial epsilon, right? I'm not going to fill that in, and partial y, partial eta. Okay. But those expressions look very similar. It's just you take the first two expressions, just replace x with y. Okay. Okay. All right, so we can take these derivatives and we can actually put them all together into what's called a Jacobian matrix. Okay. Okay. Okay, so our Jacobian matrix, let me give you the definition here. This is actually pretty important, right? And so you're going to use this definition in your final project code as well. Okay. So the Jacobian matrix for a two-dimensional problem is always going to be 2 by 2, right? So whether you have rectangular elements or triangular elements, okay? Okay. Right, so we're just basically going to have our mapping derivatives just all placed into the different components here. Okay, so top left, we're going to have partial x, partial epsilon, okay, and then partial x, partial eta, partial y, partial epsilon, partial y, partial eta. Okay. Okay. Now, what's cool about the Jacobian in 2D is that we're actually going to use it for several different things. And so it's not just going to be a one and done kind of thing like in 1D. Okay. But let's talk about the same application that we use it for 1D, right? So first thing with the Jacobian is that it always acts as a scaling factor, right? The fact that when we go from the physical domain to the parental domain, usually the area of our element is changing when we go through that transformation. Okay. So the Jacobian is kind of like a scaling factor to basically ensure that everything is still physically consistent with each other. Right? Right, so the first application of Jacobian, okay, scaling factor for changing domain size. Okay, and so that means if we have just a generic integral here in the physical domain, right? So integral of f of x and y dx dy, okay? We have arbitrary bounds because our element here is arbitrarily shaped, right? But in order to apply Gauss quadrature and kind of following the isoparametric concept, we're going to take this integral and convert it to one where our integration bounds are -1 to 1 because that's the bounds that work with our with our Gauss quadrature. Okay? So we're going to integrate -1 to 1, integral -1 to 1 of f. Okay, we're going to plug in our mappings at this point, right? So instead of x and y, we're plugging in x as a function of epsilon and eta, y as a function of epsilon and eta. Okay, so those are the mappings that we just computed. Okay, multiplied by the determinant of our Jacobian matrix, right? So this is where the Jacobian factors in, right? You have to take the determinant because you can't just plug a matrix in there. You have to get a scalar, right? And so the way we get a scalar is we take the determinant of that matrix, okay? And then we're integrating over our new parental coordinates. And so we have d epsilon, d eta, okay? Okay. So that's kind of the first application of the Jacobian. It's just that we know that our integration bounds are changing. We need some way to account for that, the account for the different sides of the domain. And so we come up with this Jacobian, and it turns out that the determinant of this Jacobian is exactly what we need to keep the size of our values consistent with the original physical domain. Okay. Okay. So this application of Jacobian is basically exactly how we used it in 1D. Okay. But this is just kind of the 2D version. Okay. Any questions on this here? Okay, good. All right, so the second application of the Jacobian, which is a little bit surprising, we actually did this in 1D as well, but we have to kind of more formalize it here because we're in 2D. The other application for the Jacobian is to act as a conversion factor for our shape function derivatives. Okay. Because when we do the integral in Gauss quadrature, right, we're kind of making the assumption, or we have to make the assumption that every function or everything that we integrate there is going to be a function of epsilon and eta, right? And that includes the shape function derivatives, right? So no longer, right? So no longer can we have partial n1 partial x partial n2, partial y, right? So normally that's what we obtain when we just directly apply our finite element methodology to our weak form, okay? We can't have that because X and Y, X and Y cannot come to the phone anymore. They've died essentially, right? All right, and so we need to convert these into partial derivatives with respect to epsilon and eta. Okay? Okay. And of course, there's more. There's technically 8 of them, right? So there's 4 shape functions, and they're functions of 2 variables. And so we take, a partial derivative with each variable, but I'm not going to write out all 8 of them. Okay. Okay. So those shape functions obviously do exist, right? And so, we have those shape functions. In fact, right? In fact, since we have explicit expressions for the shape functions up here, right? We can actually compute those 8 derivatives very easily, okay? But the problem is, right? The problem is, when we look at the weak form for 2D heat conduction and the weak form for, 2D elasticity as well, right? Those equations were formulated in the physical domain, right? And so our governing equations, okay, our weak forms were formulated with derivatives in the physical domain. Okay. Right. So if you kind of look back, I think this is obviously before the midterm, but I think it was probably the Thursday before the midterm. Um, we went over the weak form for 2D heat conduction, right? So if you look back at those expressions, you'll see that all of the shape function derivatives were with respect to x and y, right? Which makes sense because we didn't even introduce the concept of an isoparametric element back then. Okay. So we have to reconcile this somehow. So we have to reconcile the fact that, we don't have those anymore, right? So we can't compute shape function derivatives in the physical space. We want to compute our shape function derivatives in the parent space, but we need some kind of way to perform that conversion, okay? And it turns out the Jacobian, our humble Jacobian here, can be used to actually perform this conversion or help with this conversion. Okay? So our Jacobian is going to help with that conversion. Okay? And so I think that might be the last point that we talk about today, and then we'll probably call it for today. All right. But any questions on this so far? Okay, good. Okay, so how are we going to do this, right? Okay. So before we get there, let me write out the Jacobian one more time. Okay, so our Jacobian matrix is equal to, it's a 2 by 2. Okay. Okay. So what's interesting about the Jacobian is that if you look at those derivatives, right, the numerator of the derivative is our physical coordinate x and y, right? And the denominator of our derivatives here are our isoparametric coordinates epsilon and eta. Okay. We can do some I call kind of ghetto math here. And so, what if we take this Jacobian matrix and what if we take its inverse? Right? So you can take any matrix and you can find its inverse, right? And so if we do that to the Jacobian, right? So the reason I call this ghetto math is that, it's not, there's a good mathematical reason for this, but when you write it out, it looks kind of goofy, it looks kind of silly. But when you take the inverse, right? When you invert something, you kind of associate it with kind of taking its reciprocal, right? So the inverse of a number is just the reciprocal of that number. So when you take the inverse of the Jacobian, you kind of invert each of the individual derivative there. So instead of having a derivative of the physical coordinate with respect to the parametric coordinate, you reverse it now. So you have a derivative of the parametric coordinate with respect to the physical coordinate. okay? And you transpose it, right? And so let me kind of show you what that looks like. Okay. So when you take the inverse, you have partial epsilon, partial x. Okay. Next, you're going to have partial eta, partial x. Okay. Partial epsilon, partial y, partial eta, partial y. Okay. Right, so this is not a usual. I promise you, I can prove this. Right, it looks silly to kind of invert derivatives. You know, you shouldn't be able to invert derivatives like this. That's not how derivatives work. But just the math for it kind of works out, and it kind of works out kind of cleanly when you compute the inverse of the Jacobian. Okay. Okay. Anyway, so the nice thing about this is that we can use these, right? So these derivatives, especially here, are really nice because we can use these to convert our original shape functions. Okay. Or maybe convert's not the right word, but maybe the right word is to basically express our original shape functions in terms of the shape functions of our parametric element here. Okay. Okay. All right. So let's just do that. Right. So let's kind of see what that looks like. Okay. So let's start with the weak form again. So our weak form for 2D heat conduction in its very simplest form is we have a double integral of the gradient of our weighting function multiplied by the thermal conductivity K multiplied by the gradient of our temperature, okay? dA. Okay, where if you recall, right, the gradient of our weighting function and the gradient of our temperature field, they both are expressed in terms of the shape function derivatives in the physical space. Okay. All right, so I'm not going to write both just because it's a lot of writing, but let me just write one for you. Okay. So for example, the gradient of the temperature field, okay, for a four-node rectangle looks like the following. So we have this matrix here, right? So it's a long matrix, right? So you have partial n1, partial x, partial n2, partial x, partial n3, partial x, partial n4, partial x. Okay. Same thing, but all the y derivatives as well. Okay, so partial n1, partial y, partial n2, partial y, partial n3, partial y, partial n4, partial y. Okay. And this is then multiplied by our temperature, our nodal temperatures, T1, T2, T3, T4. Okay. Okay. All right, so we have the gradient of our temperature field, but remember, when we're working in finite elements, any derivative operation, it just gets passed to the shape functions, right? So when we take the gradient of our temperature field, that's just our x derivative, y derivative. We just pass that directly onto our shape functions, just like this. Okay? Okay. But with isoparametric elements, we don't want to work in x and y anymore. We want to work in epsilon and eta instead. Okay? So what we want to do is we want to come up with a way to represent each of these shape functions with the shape functions in our parametric space. Okay. Let me show you one as an example. Okay. Right, so let's take one of these derivatives here and let's see if we can express it in terms of the shape functions in our parent space. Okay. Okay. So can we express this in terms of partial n1 partial epsilon and partial n1 partial eta? Okay, so because that's what we want. Okay. Okay, so let's see what that would look like. It involves a little bit more ghetto math, unfortunately, or maybe fortunately. It's kind of interesting here. Okay. Okay. So what we can say is that partial n1 partial x is going to be the combination of both of those shape function derivatives there. Okay. So it's going to be partial n1 partial epsilon plus partial n1 partial eta. Okay. So I'm leaving a space there because we are going to multiply this by something. Okay. Okay. But we need to multiply each of those shape function derivatives so that the denominator of our expression is x. Okay. And so that means for this first term here, so we're going to multiply this first term by partial epsilon partial x, right? Because if we do that, the epsilons will essentially cancel out, and then we're just left with partial n1 partial x. Okay? And we need to do that for the second term as well. So we have partial n1 partial eta multiplied by partial eta partial x. Okay? And we can do the same thing for the y derivative as well, right? So we partial n1 partial y. We can express that in terms of our shape functions in terms of epsilon and eta. So we have partial n1 partial epsilon plus partial n2 partial n1 partial eta. Okay. I apologize. Everything is still in n1. Okay. And then we're multiplying this by partial epsilon partial y partial eta partial y. Okay. Okay. So what do you notice about all the terms there in blue, right? And I'll highlight them just to kind of, emphasize them even more, okay? Right, so if you look at all of those expressions in blue there, right? Those are exactly the entries of what we have in our Jacobian inverse, right? Right? And very conveniently, our Jacobian inverse here is also a matrix, right? And so what we can do is what we can say is that this huge matrix here, this 2x4 matrix, right, can be expressed as the product of a matrix involving the shape functions in our parental coordinates and the Jacobian inverse, okay? And I was going to write out the expression, but I think it would take me 5 minutes to write down, so we'll do that on Thursday. Okay, but I'll tell you exactly what it is here. Okay, so we can express this as a product of a matrix with shape function derivatives in the parent space and the Jacobian inverse. Okay. And that right there solves our problem. And so we can take our weak form, which has shape functions in these physical coordinates, and then express them in terms of shape functions in the space that we want. Okay. The only thing that we have to add here is just the Jacobian inverse. Okay. And it ends up being, it doesn't seem like it just because there's just a bajillion terms we have to write out for each of these, but it does end up actually being very elegant. Okay. And it's especially elegant when you actually write it in code, especially in MATLAB. So this is actually very fun to program in MATLAB because MATLAB does matrix multiplication very elegantly. And so, you can just multiply these, you just have to define these matrices, multiply them together, and then voila, you have isoparametric finite elements. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. So when we come back on Thursday, we will jump right into this. I will write out the full expression for you just so that you can have it in code. Okay. And then we will continue with our discussion from there. So thank you guys for coming today. Remember, on Thursday, I will have your midterm exams ready to return. So make sure you are here for that. Okay. So hope you guys have a good rest of your day, and I will see you guys on Thursday. Yeah. I'll bring it. So 4:30 pickup I probably won't finish till Monday. Okay. But I'll bring it Monday and Tuesday. Okay.
Wait, what?
Because there is a about 2D yeah, about the 2D physical function. Is it ever possible to be unable to convert it to a regular rectangular?
No, it shouldn't be because the way the shape functions we define them, that conversion is always going to be available.
Okay.
Yeah, so even for quadratic elements, it does get quite messy for quadratic elements for sure. But it is always possible. It's just the calculations are not neat.
I see. So just more complicated, but totally.
Exactly. Yeah.
Thank you.
I noticed when we use the determinant, is there any case where the Jacobian will ever be zero? Because
Great question. Yeah. So that happens when you have elements that are kind of ill-defined. And so as long as you have kind of four distinct points, then your determinant will never be zero. But if you have a situation where you have an element collapsed on itself, or like maybe one of the nodes that kind of comes in, then that can be a situation where you're zero. So that causes issues. And so that's actually a great point because people always wonder this when you run ANSYS, there'll be times when the meshing will fail. And you're always like, what does it mean? Like, what does it mean if it fails? And so when a mesh fails, it's because you have like an element like that collapse on itself. And it's impossible to actually write a calculation itself. So meshing algorithms are interesting because meshing algorithms are done. They're kind of independent from the solver. So meshing algorithms have no idea that you're going to run an FEA on this. And so sometimes they'll create elements which kind of collapse on itself, and that's what happens when your meshing fails.
what would be kind of like a physical example of element that collapses itself?
It's not a physical thing because the mesh is something that you just approximate just to run the FEA itself. So the mesh is something you're breaking up the domain kind of artificially just to do the simulations. So it's not necessarily a physical situation, but it does happen more often when your geometry is very complex. Because what happens when the mesher tries to mesh that, then it sees a complex shapes like I did jam like 3 elements in here. And sometimes it doesn't work out, and then an element just collapses on itself, and then you end up with
I remember in what I think was the first activity where